Hi there. Today we're looking at set distribution networks, a generative model for sets of images by Xuanfei Chai, Walter Tablet, Miguel Angel Bautista, Carlos Gestrin, and Josh M. Suskind of Apple. So this paper introduces a generative model for sets, and it does so in an energy-based model fashion. It will have an encoder, a decoder, in form of a generator, it will have a discriminator, and it will have all kinds of math, but the end result is a model that can generate sets of images. And by sets, we mean it can generate different kind of views on the same identity of image, and you'll see what that means. And it can generate even sets that it has never seen before, which makes it different from a class conditional GAN or something like this. So if I can't really describe it on a high level in a very concise fashion. You'll just have to stick around and see what's going on right here. So if you like content like this, feel also free to share it out and leave it a like. Tell me in the comments what you like. This is going to be a fairly math-heavy paper, and I'll try my best to kind of distill it down to what's happening, because ultimately it's not that difficult. All right, so if you have a look at these samples right here, these are examples of sets of images. Now, without actually caring for top and bottom row, they will have some meaning right here. The top row is always a row from the actual data set, and the bottom row is the reconstruction of that set. Now, you'll see that the images don't really have a correspondence. So you see it's the same truck in the top and the bottom row, but the orientation here isn't really shared or anything. And that's because, as we said, this is a set network. So what you want to do in this problem setting is you want to build a model that can take this set right here from the data set, and it can encode it into a latent description that we call Z. Z simply describes the set as a whole. So Z here would be truck, right? It would sort of be the 3D model, so not the class truck, but the 3D information of the truck without having any information of the different views, okay? And then you want to build another model that can generate from this low-level representation of the set, can generate the different views, okay, like each one of these by sort of rotating it. So we want to build a model that understands just from the pixels that here we have sets of things that they somehow always share a commonality. And in this case, they always share their 3D structure, right? What they don't share is the view where they rendered from. So our model is supposed to kind of parse the two apart and encode that 3D structure just from the pixels in this Z variable, and then encode the fact that you can rotate it and look at it from different views into the generative model that then produces the different views. Okay, and the reason why there's no correspondence between the views is we simply regard these things as sets. So our final objective is simply going to be that the set on top is different views of that particular truck is going to be very similar to the set on the bottom, which is also different views of that particular truck. And that's what our model is supposed to do. Now, you might know something like this from, we can simply say, well, this looks like a class conditional GAN, right? I simply have the class truck, and I feed this to my generator and my discriminator and my encoder and so on, and it will produce the same truck, and here that, and here the bench, and so on. The problem, I guess, becomes more apparent when you go to this different data set. So this is a face data set, and again, top row being the input and bottom row being the output. Now, what is supposed to be preserved, you can kind of see in the images, is sort of the identity of the person on the photo. Now you have to kind of gloss around your human bias here. You as a human can tell extremely tiny differences between faces, and therefore none of the actual identities are going to be preserved, right? So this on the top I believe is Ali, and on the bottom here it's not Ali. So but you'll have to sort of gloss around this, and you'll see that what is preserved, or what is supposed to be preserved, is something like the rough identity of the person on the picture, and also a little bit of the image compositions. So you see here in the background, you often have sort of these sports backgrounds, right, where there's kind of a washed out stadium or whatnot, and you can see that this is also preserved. Here I think it's kind of a glamour shots of this, must be some sort of glamour model, and you'll see that this as well is preserved. What is different within each set is, of course, the different views on the same identity, right? So you have the same person and you have pictures of them in different views, different lighting, different hairstyles, and so on. Here you even see you have the black and white image, and the set that is produced also contains some black and white images. So this model, this is already the trained model here, is doing a fairly good job. Here you can see that almost all the pictures have some sort of double, like two people with one being sort of half in frame, and it leads to fairly strange thing. I'm gonna guess the model hasn't seen lots of that during I particularly like this. This is pretty good. Also here, we know that a lot of these face data sets, they don't really have bald people all too often. So you can see here this results in sort of kind of a weird Richard Branson type picture. In any case, it does a fairly good job, right? As you can see right here. And what's the problem with these faces? Can't we just do a class conditional again, where we basically say here, this is Ali, right? And that's one class in our latent vector, and so on. What we want to do is we want to train something like this, where we can give in a new identity that we haven't seen during training. In fact, we want to train something where we don't even know how many sets there are going to be in the end, right? We simply want to train it in a way where we say, look, I'm going to give you a set, and the set will have, images of the same person, and you're going to sort of reconstruct that in a way where you output a set of images of that person, conserving the identity of the person and the rough style of the picture. So this is really different from a class conditional again, as in we don't know how many classes there are, and there can be new unseen ones during testing. So how do we go about something like this? And here's where the thing starts. So we're going to dive into a bit of the math here, and then into a bit of the reasoning. But ultimately, what they're going to do is they're going to build three things. They're going to build an encoder, a discriminator, and a generator. So what does the encoder do? And remember, our task here is going to be, the way we train it is going to be by reconstruction, at least one way we train it. So the encoder is going to take this set of images that we give it, for example here, different views of this car, and is going to produce this representation, this set representation. Now, what should a property be of the set representation? For example, it should be independent of the ordering of these inputs, right? A set is simply a collection of objects. It's independent of the ordering, and it's also independent of the size in some way. Of course, a bigger set gives you more information, but the set identity, the fact that this is this particular car, is independent of how many views you have. So what they do is they put each image through an encoder, which is a convolutional neural network, and I guess that gives them a hidden representation, an encoding, an embedding for each image, and then they have this operation called pool and binarize. And so this does two things, namely, first of all, it pools, it simply averages these things. So it goes 1 over n ci of xi, or c of xi, I guess. So this simply averages these encodings right here. And this already fulfills our property. So this average is independent of the order of the images. And also, I can add more and I can add less. In expectation, the average will result in the same thing, right? So this here, now we have basically lost the information of the order, the exact ordering, and so on. This is simply an average of these images. It's a good representation for a set. This is now, if we give enough images, this will be independent of the particular rendering position, and it will only depend on the fact that this is that particular car, if it's trained well, of course. And then the second thing is binarize. And here you have to understand how these, what exactly this set latent representation is. How do we encode a set in latent space? And as far as I understand it, what they do is they do the following. So since they don't know how many sets there are, they can't simply do the classic one-hot vector. So what you would do in a class conditional GAN is you would say, I have a vector, and maybe I have 10 classes, so I'll make 10 entries right here. Is that 10? I don't know. So if I have C classes, I'll make C entries, right? And I'll put a 0 in all of them and a 1 where my class is, or something like this. So this would be a valid encoding for a class conditional GAN to represent the identity of the class. Here, however, no, we don't know. And also, we can't really make this continuous, because if you make this continuous, you wouldn't really encode the identity of the set. You would encode more of kind of a continuous latent space, and then that becomes kind of different when you have new sets and so on. So what they really want to do is they want to make this representation here be a description of the set itself, but not a one-hot. So what do? What they do is they do the same thing. They have a vector, but not of size C, because they don't know C, but of some dimensionality D. Okay, this can be 10, this can be 4, this can be, whatever. Just let's say it's 10 again, but we don't know how many classes there are. What the model can do is it can encode each class as a binary vector, a binary combination of negative ones and ones. So it can put like a -1 here, a 1, -1, -1, 1, 1, -1, and so on. So what does that give you? Now you can encode much more than 10 classes. In fact, with this you can encode 2 to the 10 classes, right? And so it's not that they can encode an unlimited set of set identities, but they can encode in this manner. They can encode a lot, right? They can encode this many sets using a representation like this. So this binarize operation, it will take this output right here and basically clamp it to either 1 or -1. So the set will be encoded by a binary vector like this. And then the generator and the discriminator take that information, okay? And we'll go over what this architectural choice means. But right now, this you see that this is a way to encode a large number of set identities in a low-dimensional vector. All right. So there are two things now. There are the discriminator and the generator. So first of all, the generator is pretty easy. The generator's task is to take this Z that we just saw, which is the set identity, and to generate different instances of that set. right? And for that, it needs this noise here. So if you know a generator from a GAN, it always kind of needs input noise in order to produce different outputs. And that's this thing on the right here, this Z prime. They simply come from some sort of latent distribution. I think they call this P of psi, which is some like a uniform or a Gaussian or something. You just sample some noise, right? And you combine it with this thing right here, which is the set identity. You concatenate it. And then each one of these different Z will produce one different view right here. Okay? So the generator's task is simply take the set identity and combine each with some noise and produce some views of that set. Now the discriminator's task right here is going to be to decide, it's going to get a set of views of a set of pictures, and it's going to have to decide, is this set coming from the generator or is this set coming from the dataset? Right. Now you can't simply compare images to each other like you would do in a regular GAN because they don't correspond to each other, right? But what should correspond to each other is this identity, this Z identity. So the discriminator is going to take also two inputs. It's going to take this set right here, or from the data set, and it's going to take this right here, this Z. Now this Z is going to be the set identity, and that you get from the encoder, right? It's the same as you get right here. You get it from the encoder, which set you should produce, and the same goes here. So the discriminator knows the set. Discriminator knows, for example, I'm trying to produce that particular car, and it gets a set of images that is supposedly of that particular car, and needs to decide, does it come from the dataset or from the generator? So it uses the same encoder pipeline here. It's just like a CNN giving you a latent representation. And then it has two tasks. The discriminator has two different tasks. First of all, this here is the regular GAN path. So there's an MLP, there's simply a pipeline that outputs a number, and the number is, does this come from the dataset or does this come from the generator? But then there is an additional pipeline that they have found to be vital to train the objective, which is a reconstruction pipeline. So this is more like a sort of like an autoencoder pipeline where they have a decoder, they try to reconstruct the input set, and they then compare it using mean squared error. Now here, they try to reconstruct the input set really picture by picture, not as a set, but picture by picture. So it's different from the set generator, okay? And this pipeline is just to stabilize the training, but it also goes into this the output of the discriminator. So sort of the discriminator is happier the more it can reconstruct the images, which seems kind of weird at the beginning, but they say it has helped in other GANs. I'm not super familiar with GAN literature, but it's just another objective that you can add. So this is going to be the overview right here. So if everything works well, we should be able to take a set from the dataset X, right, which is going to be different images from the same person. We should be able to feed that to the encoder, get a latent representation Z for that set that somehow encodes here the identity of the person. And now if the encoder works really well, we don't have to have seen that person before. It will simply somehow encode the identity in that binary vector. Then we feed that to the generator together with some noise, and we'll get out a set of pictures of different views of that same person, or the person with a similar identity, and pictures with similar kind of picture style. And that, if our discriminator works well, will look very, very similar to, or will be images really of that same person. And our discriminator, if we plug that in right here, will agree. And we plug in the z right here. Okay. That's the overview. Now the math. So they go about this in this sort of probabilistic framework. What they say is we denote an image set of size n as x, and that it comes from the space of sets of images. So capital X right here is going to be a set of images, as you see here, and this here is the space of all sets of images. Okay, so what they want to do is they want to build a probabilistic model of that. So a model where you can input a set and it'll tell you how likely is that. Now, you don't actually have to have a number as an output right here. What they often do is they start with a formulation like this, and what they end up with is simply a model that allows you to sample from this distribution, right? From which you can estimate the probability. But ultimately what we want is a generator that can sample from this. Okay, so how do they build it? They decompose this into two parts, and this is just a decomposition. This is standard decomposition of probability, where you'll say, okay, what's the probability of a set X? The probability of a set X is the probability of the latent code of that set times the conditional probability of that set given the latent code. So already we ask ourselves, what's the probability of X? And what we might ask is, well, X, if I look at X, it has these different images of this. It has these different images of that thing, whatever is on the image. I can first ask, what is the probability of that particular thing on the image? And then conditioned on that, what is the probability that I'll get these particular images, right? This simple decomposition already kind of builds up this model of encoding, decoding. So we'll go through that step. This here is going to be a deterministic function, our encoder, and this here is going to be a probabilistic function, the decoder. And it's probabilistic because every time you call it, basically, every time you call the generator, it's going to give you a different output because you're going to feed it different noise at the beginning, okay? So this is going to be our encoder here, and this is going to be our decoder. So they say here X is Z is a deterministic function that maps a set X to an element in a discrete space, Z, okay? This is a discrete space as opposed to maybe a regular autoencoder where you have a continuous space. So here we want a discrete space. And a lot of mathematical problems are going to arise from the fact that this Z is a discrete space and not a continuous space. So here P is a prior distribution with the support given by sub Z, which means all the Z vectors that have some sort of set associated with them, which is a subset of all the Z. So that basically means that if we have a given encoder, not all of these binary vectors are going to be filled. Even, if we plug in all the world's faces into our encoder, it might not fill all of the binary capabilities that we have. So this prior is only defined on this support of this. And here you already kind of see what kind of mathematical hurdles you have to go through if you do something like this. And all the math here is most of the math here is going to deal with the fact that we have this discrete thing and so on. And a little bit of a caveat here also is that this here, they mention this here, is you need a prior distribution on your Z variables. And this is also not easy. So really quickly, What does it mean to have a prior distribution on this kind of thing? Because usually in a regular like autoencoder or variational autoencoder, right, your latent code, you'll have a prior on it, and that prior can be, you know, some continuous thing like a Gaussian, and even in a regular GAN, as I said, you have your noise distribution and so on. What is a prior on that thing? Now you can say, oh, a uniform prior, but again, we would like to learn this prior such that it matches the data set well. Now they use a prior from a paper that's called MADE, M-A-D-E, and really quickly what it does is it sort of kind of decomposes this thing. So what you'll have is a neural network that outputs binary vectors like this, and it will sort of output them in a fashion auto-regressively. So it will output one of them, and then conditioned on that, it will output the next, conditioned on that, it will output the next. And this is such that the probability of this binary vector, -1, 1, 1, -1, and so on, is going to be decomposed into the probability that there's a -1 here, times the probability that there is a 1 here, given that there is a -1 here, and so on, and in different order. I don't really want to go into this, but just to show you that there is a lot of consideration, of mathematical consideration, if you really want to go about this sort of thing in a formal fashion. So they define two things. First of all, this prior, okay, it's a prior distribution that they can learn from the data set. And then there is this conditional distribution, this what you might call a generator, right? If you're given a Z, one of these binary codes, what's the probability of a given set? So I tell you here, it's Scarlett Johansson. What's the probability of these pictures being different views of Scarlett Johansson? So that is going to be simply, we're going to build this as an energy-based model. You can do this. What you'll have to do is you'll have to define an energy, and we'll just quickly discuss what that is. And then you can build a construct like this, where you'll say the probability of a given set is going to be the energy that assigned to that set divided by the energy that I'm going to assign to all of these other sets. So it's a form of an energy-based model. You can phrase very many things in terms of these energy-based models. And Yann LeCun gave a talk about this at iClear, I believe, where he gives a lot of different examples of energy-based models. So I invite you to check this out. I've also done a video on some of these energy-based models and what you can do with them. Here, it's simply to define this probabilistic model. So what we need to do are two things. We need to know what is this energy. So what is this energy supposed to do? This energy is going to be a function that gives you, and now I have to think, so its energy is going to be a function that gives you a high value if you are unhappy with the input, and it gives you a low value if you are happy with the input. Okay, so you see the negative exponential here, which basically means and also the energy is always positive. So the best, if you are super duper happy with what your input is into the function, you'll output 0. So if you output 0 here, you'll see that e to the exponential function of negative something is going to be quite small. And no, maybe I have it wrong. Maybe you output a really high number when you're really happy. I'm not sure, but it's one of the two. So this comes from a physics background. No, I'm right. So if you're not happy, you'll output a super high number here, which will make this negative exponential be really close to 0, and therefore the probability, you say, if I'm not happy, the probability should be close to 0. However, if you're really happy, you'll output a low number right here. Now the energy always has to be greater or equal to 0, but the lower you go, the higher this probability is going to be. The bottom thing here is simply to normalize the distribution, because in a probability distribution, you always have to normalize, because otherwise it's not a probability. And this is what most of these models basically are fighting over, how to normalize the distribution. And what we're going to do is simply normalize it by sampling, which is what most of these things do. You can build energy-based models without this, which GANs are a variant of that. But okay, so what we need to do is we need to come up with this energy function that is going to be a high number when we're not happy with the input. Now, what is the input? The input is x and z. X and z. What does it mean we're not happy with the input? It means that the image x, and you see x here is one of the images of the set, that particular image isn't really congruent with the z, with the identity. So you say, well, this isn't really a picture of Scarlett Johansson. So I'm going to assign this a high value. However, if this is really any sort of picture of that person, then you're going to assign it a low value. And how better to do this than to build a neural network to do that? And this is going to be our discriminator. So our discriminator is going to take the role of this energy function. Okay? Cool. Now, I said you need to normalize, and I kind of said it off the cuff and so on. But the problem here is, again, we have this kind of sets and so on. So our probability, as you'll notice, is the probability of x given z. So we are already given the identity of the person. So what do we need to normalize by? We can't simply normalize by all the sets of images in the world. Like here, it's in the integral. We need to normalize by all the sets of images that are mapped to that same identity. Okay? So in order to normalize the distribution, we'll basically ask, how likely is this set? How happy are you with this particular set right here, compared to all the sets that could exist that would map to the same identity? All right, that's why these indicator functions are here. And as you can see, the part here is simply a normalization, where you say, I'm just going to produce I'll consider all the other possible sets of images that map to the same person, and I'll simply divide by the energy of those. In fact, if you do it correctly, this particular x is also in that particular set, but usually it's going to be a fairly small part, but to properly normalize, of course, you have to consider it as well. Now, this bottom part here, as I already said, is going to be the main problem of most of these probabilistic methods. And as I already said, again, it's usually approximated by simply sampling a bunch of these sets, and not by enumerating all the possible sets of images. And this sampling is going to make some further problems, as we'll see, I guess, down here. So here is what we optimize ultimately. We optimize, or one of the things we optimize is, or are we? Okay, yeah. So they say we apply maximum likelihood estimation to estimate the parameters of the thing we just defined, where the negative log likelihood loss for an observed set in the training split is this. So this is simply the negative log likelihood. The log decomposes into a sum. So this is going to be your prior, and this is going to be your generator discriminator combo. Okay, it's the generator producing images from that binary code, and then the discriminator assigning high or low values to that produced images, and also to images from the dataset. And the thing over here is simply going to be the prior over the z distribution that we briefly discussed. Now, again, they have to do some tricks here where they say, okay, we can get rid of this support by using a normalized distribution over z, which is a bound on that true prior and so on. So they're going to replace the p with a p bar, which is over the entire space of z. And that's going to be a bound. But the interesting part, I feel more, is here, where they consider the loss, again, of this conditional distribution on z. So you'll see the exact same quantity right here, but now our loss is going to be the negative log of that. Now, since it's the negative log, you can decompose the division into a sum. And this part up here, you'll see the indicator function here is a bit unnecessary, because the z here is the z that we're considering is going to be the z of that particular set that we're considering, and so this equality holds on the top. So disregard this. And this down here, as I said, is simply a filter to filter the space of all sets to the ones that correspond to the z that we have in the energy function. So this goes here because it's simply a log of an exponential, and the negative signs cancel, so you'll end up with this. What does it mean? You want to minimize this loss right here, and part of that is going to be you want to minimize the energy function of these inputs. Okay, you want to, and this is now the case when it comes to from the data set, right? So when x and z come from the data set and e is your discriminator, then you want to make the output of the discriminator really small, which means that you want to train the discriminator to say, I'm really, really happy that this particular image comes together with this particular identity encoding. Now, if it comes from the generator, of course, you want to do the exact opposite. You want to assign it a high value. Remember, energy low means happy with the input. Okay. And then the normalization down here is, as I said, the problem. So you'll see it stated right here because it's under the division. It's going to pick up a negative sign, which combines with this negative sign, which gives you a positive sign right here. Now, this part right here is going to be intractable because it's not going to be feasible to enumerate all the sets of images. It's not even going to be feasible to enumerate all the sets of images that just correspond to that particular identity. And in fact, it's not even going to be feasible to sample from that because we have no clue, right? We can't simply generate out of the ether true other pictures of a particular person. What we can do, of course, is we can use our model to produce more images, right, of that particular identity. So what we'll do is we'll replace this distribution with a variational distribution and we'll sample from that. Now, this isn't exactly the same. This isn't this log probability anymore. And that's why, first of all, we have a bound here and not an equality. This is called a variational approximation. So we bound this quantity. And we can only bound this quantity if we down here introduce the entropy of the variational distribution. This is a fairly standard trick in variational approximation methods. If you want to look more into this, look into kind of VAE explain, variational autoencoders explained, or anything like this will teach you how these methods work. And in case we replace a distribution with a distribution we can actually produce. And what is that distribution? Look, what we're supposed to do is we're supposed to produce a set of image given, so sets of images here given particular z. And we can do that. That's our generator, right? So we can use our generator to produce those samples. And that's what they say here. Here we have derived a lower bound by introducing a variational distribution, which we parameterize in the form of a generator. Okay, so the generator is going to produce that distribution. It's going to use this noise production. So as you know, the generator takes two things. It takes the identity encoding and a bit of noise and is going to produce an output set, or for each noise it's going to produce an output image. Very cool. So that's the kind of math formulation behind this model. Now, they have a model architectures right here, but this is all fairly standard, except for the prior, they learned the prior on the Z space. So you see you have Z being this binary vectors. They say we use a standard autoregressive model made with 3 fully connected layers, mainly for its simplicity and robustness. And so again, maybe it took me a while to get what this prior does. This prior is supposed to say, it's not in a GAN, you have the Z vectors always being some sort of from the standard noise. But what you can also do is you can learn better noise distribution, a better input distribution for your GAN by basically making a GAN for your input distribution. So what you'll do is you'll have a Z0 right here, and then you'll learn a GAN to learn better input distributions. Okay, and this is what you do here with these with this prior on Z. This is more standard in like VAEs than it is in GANs, but it exists. So encoder, say as a necessary option, encoder for a set needs to satisfy the permutation variant property. We opt to use a simple architecture design where we let this be the average right here. So as you can see, this is the average, and then they use this binarize operation. And the binarize operation here is clamping the values to 1 or -1, and it is a straight through estimator, which means that you back prop through it as if you hadn't clamped, but you forward prop through it with clamping. This is kind of a trick to get through discretization things. Discriminator's job is to assign low energy to observed images and high energy to generated images. Given a set code Z, we use an autoencoder-based energy function implementation similar to 25. And here they say, we have found that this choice is important as it enables effective learning in early stages of training. So that's why they do usually a discriminator the energy would be equal to this thing right here, which is a small MLP that maps the input to a real, sorry, you can't see that maps the input to a real number. Either high energy, I'm not happy, low energy, I'm very happy. Here they also include this thing right here, which is a decoder. So it's kind of a, you can maybe think of it as another little GAN, another little generator, or the generator part of a VAE or of an autoencoder, sorry, not a VAE, an autoencoder that takes as input the encoding of the particular image and the identity and is going to produce something that's close to the output. Again, observe that this is now with respect to a particular image. So here we're trying to reconstruct that particular image because we have its input thing right here. And it's not the same as the generator that is just asked to produce some view, something that corresponds to this particular identity vector. Okay, the generator generates a set conditioned on a set code by sampling in random variables, each of which is concatenated with Z, and generates an image independently. Cool. So, the losses, they now introduce some margin losses on the things here, but basically you can just translate what we have on top, where we formulated the negative log likelihood, into the losses right here. They do have some simplifications. For example, this to train the prior, to train to train the encoder, I think, you have to make a bit of an approximation in that the encoder is supposed to match this z vector, right? And that's not differentiable by itself. So they have this sort of L1 approximation right here. They leave away the entropy from the loss, and they have found that to work well. They introduced this margin losses right here. I don't want to go into that too much, but basically they simply, in a way, with some approximations, they approximate, oh yeah, here it is, the indicator function. They approximate it as this. I was looking for that. They optimize this log likelihood from above in the way where they always optimize, they keep the generator constant and they optimize the rest of the pipeline, so the encoder and the discriminator and the prior, and then they keep that rest fixed and they encode the generator. So what does that do? Before, remember right here, we had this approximation right here where we said, you know, what comes out of this, we're not really optimizing this, we're minimizing a lower bound on it, right? So here's a quantity that we want to minimize, but here's a lower bound, and we'll just push that lower bound down by optimizing. Now, that doesn't tell us anything about this thing right here, but there is actually more to it. So by optimizing the discriminator and the encoder and so on, we do minimize this lower bound. So this loss right here, you see this energy function, we'll adjust that whenever we adjust our that particular loss, our discriminator, we'll adjust that energy function. Whenever we adjust our encoder, we are going to adjust the part that generates the z vectors right here. So we'll push this down. But whenever we optimize our generator, that's when we make this gap here smaller, okay? So we always do two steps. First or second, in one step we reduce this, and in the other step we'll bring these two closer together. And as a result, of course, we hope that it's not just the bottom one going to up, down, up, down, up, down, but we hope that both of them reduce with time, because the top one is the one we'll actually want to reduce. That's our actual loss, or our log likelihood. And that is, I guess, going to happen in practice. So what does this do? So as we already saw, here on top you have a set, and you feed that through the encoder. You feed that through the encoder. That gives you a z identity, and then you feed that to the generator, and the generator, you can ask it, you don't have to produce the same amount of images, you can produce any amount of images you like. They just chose to produce the same amount. There's no correspondence, but you see it's the same truck. And here they manually align these. So they just produce a bunch of images. On the left is the data set, and on the right, I guess they just produced like 100 images and then selected wherever the car looked like the closest to. So they ordered them by hand. And that is to show that, for example, look at the lighting on the car right here. It's fairly similar. I guess this one has red tail lights and the other one hasn't, but you can see that the different views are pretty well captured by the generator, and that just from all of these are created from one binary encoding of this here. So this is binary encoded to Z, and then all of these different views are created. There's no image correspondence. So that's pretty cool. And another problem when you have with sets is, how do you evaluate sets? You can't go and check for images or image closeness and so on. So they have to do some 3D modeling. They actually take these images right here, and they have to approximate their 3D shape and then compare that 3D shape with the 3D shape of the original thing in order to just quantitatively estimate how well they're doing. In the faces, the same thing. You input the top row into the encoder and you get back the bottom row. We've already looked at that, but again, to evaluate this, you actually have to go and use some sort of a face detector to recognize, is that the same person always? And is it, so you can evaluate two things. You can evaluate, are these right here all the same people? So you can have a face detector kind of tell you whether or not these are the same people. And the second thing is, are these down here the same person as these up here, right? So those are the kinds of things how you can evaluate this. And they've done this, and it's fairly interesting, and the results here are not surprising when you look at the images. So these are curves from this face detector, and of course for real images, as you can see, this is simply the performance of the face detector. So you do get some false positives if you want more true positives, right? So this is a standard curve right here, because these face detectors are not perfect. So in a given row right here, even if that's from the real data set, the face detector would sometimes fail and say, no, that's not the same person, even though from the data set you know it is. Though to match the actual child photo from Ali with his adult photos is even like, you can forgive the face detector. So that's sort of the gold standard we're trying to achieve. And you can see within the reconstructed sets, that is achieved fairly well. So compared to uniform samples, this is, fairly cool, fairly close. What is less close is this recon and real. And I believe that's when you compare the identity of the real row with the identity of the reconstructed row. And that's here. So that tells you already that the model doesn't always preserve the actual identity as seen by a face detector. And I don't know what to say except yes, that's what you see in the data, right? Also, you see that free samples, I guess. So you can do two things, right? You can give it a set, like a row, and encode that into the Z, and then you can decode that again and basically reconstruct, or you can just sample. Since you've learned a prior on the Z variable, you can simply sample. You can simply say, give me some new identity, maybe that I've never seen before, right? You have some binary vector, and now generator, please give me images of that identity. And these two here are actually sampled like this. And you can see again here, it's remarkable that within the same row, it's pretty much the rough identity of the person is conserved, right? And these are these free samples right here, I guess, and they do better than whenever you compare the reconstructed and real, but they don't do as well as when you actually input a real data and then reconstruct this. So this might be an indication that this prior isn't really working, all too accurately. And I do have my problems with this binary encoding right here, because maybe I'm misunderstanding something, but if you have these binary vectors, as we said here, the reason why you do one-hot encoding in class conditional GANs is you could simply say, what am I doing a one-hot encoding? I'll simply say z equals 3 for class 3 and z equals 4 for class 4. Like, it should be so easy. Why am I doing one-hot? And that's because these models see everything in a linear fashion. So if I have class 3 and then I have class 4 and then I have class 9, the model doesn't see that as 3 different classes. The model sees this as these two are somehow closer together than this, right? So the reason why we do one-hot vectors is that the model cannot do this. The model has one independent dimension for each of the classes, and whenever that particular dimension is high, then it knows that that particular class is activated. what this binary encoding here does is sort of, it goes back to this thing right here, where it says, okay, there are all of these different categories here. It's like you have mini classes, and the identity of whatever set you consider is now encoded in these mini classes. So I'm going to guess the first thing here might be something like, does that person have blonde hair? And the second thing might be, does the image look generally bright, or the image set as a whole look generally bright or dark, and so on. So I'm going to guess these things are encoded here, and it'll sort of just end up being kind of a discrete GAN or a discrete autoencoder rather than what they believe. But maybe that was their goal all along, and I'm misunderstanding right here. I just don't think this binarization gives you this sort of hoped expressiveness. I think there's still a lot of dependence of whether or not a particular thing is on or off. Okay, but enough ranting right here. I want to look at some more of the samples, because I've only shown you the reconstructions. What I also find interesting is the free samples. So here you can see uncurated ShapeNet samples, and on the left, so here you can see this effect from the learned autoregressive prior and a uniform prior on the right. And here you can see this effect of learning this prior. So if I learn the prior, it's going to give me back fairly okay objects. If I don't learn the prior, but if I learn the prior, if I learn the prior really, really well, that basically means I'm only going to ever produce sets that were in the training data, right? If I learn like a perfect prior, I'll see like, wait, this, this particular identity here never shows up, so I'm not going to output it. And the uniform prior might actually output it, and the generator is not going to be trained on that uniform prior, so it's just going to give you kind of crap. And here in the faces you see the same thing. Now again, what I think, I don't think that's happening. What I think is happening is encoding these kind of micro characteristics, not per se identity, but it's encoding probably, hair color, whatnot, head shape, and so on, things like this, and in each of these dimensions, and that's what is then going to produce. So each row here is one sample from that prior on the left is learned, which you see is working pretty well in terms of the output, and on the right you see it's from the uniform prior. Now, you also see here, first of all, that approximately identity is preserved, but not as much in this uniform prior. That's first. And second, you'll see that the images are much worse, which means that the generator doesn't have as much training on that particular thing, because I guess it comes from a prior that it hasn't seen during training. All right. And here, lastly, they have reconstructions if you give different number of views. So the top row, I guess, is the input. This row is when you just have 4 different views, so I guess just the first 4 or something like this, input. And the bottom one is when you have the full 8 views. And you can, I guess, see, or even more, that this increases with number of views. So the accuracy of this identity increases the more views you input of the set. And they have a bunch of other things right here in the appendix. I do invite you to look at this, and I hope you sort of saw into a bit how you would go about something like this. I found it quite challenging, the math, because I'm mainly not used to this kind of variational math, but I hope this gives you sort of an impression. All right, this was it from me. Tell me what you think, and I'll see you next time. Bye-bye.